Doing every challenge question, part 46. This is Corpio 2, chapter 3. And yes, this is the one where I just get to do some integration. It's great. Best chapter in the book. I decided to have some fun with this. If you haven't seen my integration by madness video, you should watch it. This is integration by parts. This is integration by triple parts. Integration by madness explains this and gets a bit further than that. You should watch it. It's a good video. Anyway, this, of course, is a triple part because it's e to the minus x times sine times sine. So if I pretend that e to the minus x is u dash, that means u is just minus e to the minus x. V and w are going to be sine and sine, so that means the first term is just minus e to the minus x, sine, sine. Second term is minus the integral of minus e to the minus x cos, because sine differentiates cos, and then sine, and then likewise here. This is just two lots of that thing, which is cool, and two lots of sine cos, the minuses all cancel, of course. Two lots of sine cos is just sine 2x, so that's very useful. This integral doesn't seem too bad to do. I'm just going to integrate it using integration by parts, just the basic one here, where integral of that, and then leave this one alone, and then integral of that, differentiate this one for a 2 cos 2x. And now I'm going to use the double angle property of cos to say that 2 cos 2x, I believe, is 2 minus 4 sine squared of x. I just Googled the double angle formulas and rearranged that. I probably should have written them in the space here, but I couldn't be bothered. This, trust me, it turns out to be this if you just Google the formulas. The minuses just go away here, that's fine. Now, if you expand this out, you get plus 2 lots of the integral of e to the x minus 4 lots of the integral of e to the minus x sine squared of x, which is amazing, because that there, if I've defined this integral to be I, is just I as well. So that's pretty cool. This integral is easy to do. Add 4i to both sides, factorize out minus e to the minus x, divide by 5, and we end up with this here, which I think is good to go. We just need to validate it between 0 and infinity. And when you put in 0 to this, e to the minus infinity is just 0, so it's just 0 times something, so the entire first thing is just 0. And when you put 0 in, you get minus a fifth lots of 1, because e to the 0 is 1. Sine of 0 is 0, sine of 0 is 0, and then just a plus 2, and you end up with minus a fifth times 2. But of course, that's the minus bit, because you're taking away the second half of it, so you just end up with positive 2/5, and that is that question done in a funky way. These questions are easy because they literally give you the thing that you're supposed to use that makes it really easy. Dx sec differentiates to, this is in the book, it differentiates to sec tan or tan sec, because it's 1 over cos, which is cos to the minus 1. If you use chain rule, you bring the minus 1 down to make minus cos to the minus 2, and then you times by the derivative of cos, which is minus sine, the minuses cancel, and you end up with positive sine over cos squared, which is sine over cos, times 1 over cos, which is tan, times sec. So that's kind of the derivative there, did in my head. That's fine. So we're going to put that bad boy in for dx, and we're going to replace this x with a sec theta, and x squared minus 1 with a sec squared theta minus 1. Now, this is very good because the secs go away, and sec squared minus 1 is just tan, based on that Pythagorean identity that we sure know. The root of tan squared, is tan squared. The root of tan squared is tan. Everything cancels, and you end up just getting theta plus c, where theta, of course, is arc sec, based on this relation here. And that'll be that question done. Next one is basically the same. You do the same substitution here, you get the same stuff here. This is still tan over sec, which means you end up with 2 tans and no secs left over. Now, the integral of tan squared is kind of interesting. You can memorize this one if you want to. Alternatively, just know that tan squared is, of course, going back to here, sec squared theta minus 1. And now we all know that tan differentiates to sec squared, so therefore sec squared integrates to tan, and 1 integrates to theta, of course, and you just end up with this here. You can put back the theta as arc secs, and you'll get this here, and you'll be done with that question. Really, really nice. Integrals by completing the square is what's going to come next. We're going to complete the square on this denominator here, which is super useful because then we have this relation from the formula book, which is that this thing integrated is this thing here. Now, this looks a lot like this, but not quite. So let's make a quick substitution. U equals x minus 4. And that will just turn this into a u squared, which is perfect. And now this 8 here obviously can just be written as 2 root 2 all squared. So that's pretty cool. Of course, when you differentiate this, it's linear, so this just gets replaced with this. And that turns into 1 over 4 root 2 log of u, because we're in the u world, minus a, which is 2 root 2, into plus 2 root 2. And of course, you can replace the u's with x minus 4s now, and you're going to get this answer here with a plus c on the end, I guess, if that's really necessary. The next one, also kind of cool. I decided to just factorize out the 2 from the first 2 terms, then complete the square, and then multiply the 2 back out again, eventually get to here. And then this is a slightly different looking integral. I decided to factorize out a half here, just because I know that I need a single term squared here, because if I use the substitution here, and now this is a +1 on the bottom, it's subtly different to this one that had a minus here. It's got a plus here. So I think this is the one to go with, where a is √9 over √2, or just 3 over √2, and x squared is just u squared, right? So I think I can put that in there. I'll get this with a half, of course, out the front from here. This √2 can bounce up to here to make √2 over 6 at the front, and then it's just arctan of this over a, which I've already said is is 3 over √2. The √2 can bounce to the front again, and replace the u with an x plus 1 again. Put a plus c, and you'll have the answer to this question as well. They've done this a few times, haven't they? This question, this mean value, the mean value of a function, is just a thing from FP1, I believe. So this is the thing you'll see. If you're interested in this, go ahead and read the FP1 book or watch some videos on this, but this is a well-known thing that you have to do lots of if you choose to do that book as part of your further maths. Anyway, let's just do this then on this function here. So a and b are 0 and 2 respectively. So it's going to be 1 over 2 minus 0 of the integral between 2 and 0 of this function here. So that seems pretty straightforward for us to do. Just integrate it. We all know how to integrate, put the numbers in. We all know how to do that. And we'll get the mean value of 4. And then it's saying verify or state the value you can put into the function to make the function equal this, which we just found out is 4. So now we're just looking for f of c to equal 4. F of c is, of course, just what happens when you put c's into here. The 4's cancel, so you get 3 solutions here. When you factorize up the c a couple times, you get c is 0, c is √2, and c is minus √2. Except minus √2, look at the definition here. C has to be between a and b. It has to be in the interval a to b being between 0 and 2. So c can't be minus 2 because that's outside the interval. So you actually have these two solutions of 0 and √2. And that's when this function attains its mean value on that interval. Give an example of a function which does not attain its mean value on the interval 0, 2. So any function that, well, not any function, but the things you should be looking for are discontinuous functions that don't behave so well and don't gradually move from one thing to another. So for example, if you take the function that's just 0 up to 1, and then just 2 up from 1 to 2, this function has mean value of 1. Now, if you really want to, you can integrate it and via this rule or whatever. But the mean value is just saying what is its average value in interval. If it's 0 half the time and 2 half the time, its average value is 1. So I'm just going to state that without doing the proper integral. But of course, this function never actually has the value of 1 because it goes from 0 straight to 2. So this function here, which I guess is a piecewise function, defines like this. This is horrendous, and I should not have done this. This should be a less than, I guess, or a greater than, just as long as it's not strict. Anyway, that's kind of the idea in this question, and that'll do there.